We can't hear you if you're saying anything.
It's because I had the mic off. That's hilarious. Yeah, so to recap, hi, I'm Jonah. David Wagner's at a conference this week. So Tanya and I, the two co-heads, are giving the lecture today. Midterm logistics happening this Thursday, 7 to 9. If you haven't filled out the accommodations form and you need an accommodation, please fill it out. And check Ed for details about review sessions. Yeah. So today, we're going to do introduction to web. What is the web? Most of you are probably using it right now on your computers instead of paying attention to lecture, which is fine. So we'll talk about sort of how the web is constructed briefly, and then we'll talk about some security. Brief history of the web. The web was not designed with security in mind. So a lot of our design decisions that we made were like for functionality. I think the web was designed by a bunch of non-CS PhD people to like share around papers between universities. And it was definitely not built for the types of dynamic like JavaScript enabled apps that we see today. So there's a lot of like did not design in security from the start things that we have to account for. The first era of websites, sort of Web 1.0, for about the first few years of the internet, only contained static content. So there was text, there was images, but you couldn't like click a button and have like confetti show up on your screen, place an order. In 1996, Sun Microsystems releases Java. The Java programming language was originally designed to embed in a browser and sort of run interactive content with your websites. And Sun built a browser that could do this. It could fetch JavaScript code from a server and it could execute it and make changes to your page. But the problem is that Java was far too powerful. It could do everything that a local program could do. And the end result was that opening a website on this browser could lead to like major security problems, as though you like downloaded a new program that was a virus, right? So later on, we see Netscape Navigator. They want to add some interactive content as well, but they're looking at this and they're like, okay, I got two choices. I can either take Java and run with it, or I can try something else. And they went with plan B, let's try something else. So JavaScript has literally nothing in common with Java, except the name, the general syntax, but it took the same name, JavaScript. It's confusing. It is what it is. JavaScript did take off. It's now very widespread. Many server projects are even built with JavaScript. And a lot of programs that you probably have on your computer, like Discord, Slack, VS Code, are actually just like browser windows that are running JavaScript that are embedded as a program using another program called Electron. So JavaScript is very ubiquitous. It's being used all over the place. JavaScript is kind of a bad programming language. It was thrown together over the course of like 1 or 2 summers. The result is there's no good type system. If you try typing the integer 0 is equal to the string 0, it will tell you that that's true. There aren't integers. There's only floating point numbers. There's a bunch of other random pitfalls. Takeaway, JavaScript is a very important language. You'll probably work with it at some point. But if you have to use it, consider only using the good parts, the stuff that works well, or using TypeScript, which is like a typed variant that solves many of these problems through like compilation ahead of time. There's this image. This is the like JavaScript guide, and this is the good parts of JavaScript guide. The difference in size. Okay, so that being said, what actually is the web? Someone asked if this is in scope. For the midterm, none of this is in scope. For the final, anything that's not on blue slides is in scope, and obviously anything on blue slides is not like for every semester. I know this template's a little bit different. I'm trying something new, but it's the same basic premise. So what is the web? The World Wide Web is basically just a collection of different data and services. It has services that are provided by web servers, and they are consumed and accessed by web browsers. So you know the story, you do this all the time. Your browser sends a message to a server. The server shoots you back some website. You get to look at that website, you get to interact with it, and you have this sort of communication going on with this server. The web is not the same thing as the internet. If you kind of think about it in terms of layers of abstraction, there's two distinct layers here. The internet is dedicated to making sure all of our packets, all of our messages get from point A to point B. The web is built on top of that. We assume we can already do that. And it's about how do I do things like load applications and content on top of this internet. So this is a series of protocols to enable that. It's not like networking itself. We'll talk about that in the last unit of the class. Some elements of the web. We're going to talk today about URLs, which are a way to uniquely identify data. We're going to talk about HTTP, which is the standard for how web browsers talk with each other. And we're going to talk about some stuff that a website can have. So some ways to mark up your website, ways to style it, and how to write scripts for it. So first off is URLs. URLs uniquely identify a piece of data on the web. URLs uniquely identify a piece of data on the web. We can see that it stands for Uniform Resource Locator. You don't need to memorize this, but it kind of helps to think about it based on this, because if we sort of tear this down, uniform means like we're providing a standard interface, right? We're providing one way to do a bunch of things. And their goal is to locate resources. What's a resource? Pretty much anything your heart can desire. It can be a website, it can be some data, it can be an image, it can be a PDF. So our goal is we want to have some interface that is generic enough to identify any resource that we can think of on the internet and sort of interact with it. So we divide our URL up into parts, and we'll talk about each of them now. And the first part is the scheme. It's located on a URL right here before the double slashes, and it describes how we're going to get our data. So the most common scheme that we're going to see is HTTP, and then there is a secured variant of HTTP that uses some of the cryptographic stuff we've talked about in the last unit. That's called HTTPS. They're the same protocol, but one of them implements cryptography and the other one doesn't. These are the two most common things you'll see here. But again, our whole thing with URLs, they're meant to be very broad. They're meant to do whatever. So there's a bunch of other protocols that also exist that you could use if you're not worried about the web, but we are worried mostly about websites for this lecture. And then you have the domain. The domain is right after the double slashes. In this example, it's tune.cs161.org. It defines which web server we're going to contact, right? So if we think about the web in terms of a bunch of individual servers that are each serving some content, the protocol is going to tell us how we're going to talk to the server. The domain is going to tell us which server we need to talk to. And it is written as several phrases separated by dots, as you can see there. There's also the location. The location includes the domain, but it's a little bit more broad. It has support for usernames to identify a specific user we're going to talk to on the web server. This is almost never actually used today. But for like FTP, for instance, for file transfer protocol, which we won't talk about in this class, you can basically say, OK, I'm going to go talk to a server. Here's my username. Give me some files. And then you have a port, which is a way of identifying one specific application on a web server. So if I want to go talk to Tanya, for instance, over the internet, I can find Tanya's like domain. But then if I send her packets, her computer is not going to know what to do with them, right? It's going to say, OK, I have Discord open, I have Slack open, I have YouTube open. Where should these packets go? The port's going to tell us which application to actually route our packets to. And if we don't include one, the default is always based on the protocol. So the two we want to know for this class are HTTP, which is going to give us port 80 if we don't include one, and HTTPS, which will give us port 443. So we can see here, this example does not have a port. So it would be 443 because we're using HTTPS. You need to have a domain. The other stuff is optional. Then there's the path. The path comes after the first slash, and it tells us which file we're going to fetch. So if we think of the web server sort of as a file system, the path is going to tell us where we need to go in this file system to find a specific file that we want. So if you look at this first example, we can look for avian.html in the exorcist folder here on this website, and this will try to query that and pull up this HTML file. Now again, URLs are about finding resources. They can do more than just finding files, which we'll see here. URLs can also take in a query. A query is located after a question mark towards the end of our thing, and it can supply arguments to a web server for processing. So a URL can refer to a file. A URL can also sort of refer to a function, basically. You can think of some URLs as offering up a function that takes in some arguments and dynamically provides a result. So an example here is if you, I don't actually think this URL is real, but in this case, we have some draw function that would take in a character and a size, and it would presumably return to us an image when we try to go to this URL that draws what we want. Arguments are always supplied as name-value pairs, and they're separated by ampersands. So here we have two arguments. First one is the one immediately after the question mark. Its character and its value is Evan. Then we have an ampersand to delineate, and its size and big. Parts of a URL, again, fragments or anchors. A fragment is the last thing we'll sort of talk about for URLs. And the idea here is that this fragment does not get sent to a web server. And the point of a fragment is to supply some content to either JavaScript or to the browser itself without sending it to the server. So most commonly, you'll see an anchor used to scroll you down to the page to a certain heading. So if you go click on the little copy button next to any of the headings in our textbook, it'll add a little anchor on there so you can jump straight to it. This is the most common use of an anchor by far. So another thing we need to talk about when we talk about URLs is URL escaping. URLs are meant to contain printable, human-readable characters. This is the ASCII set of characters. So if we want to include something that's not ASCII in our URL, we have to get a little creative. This solution is called URL encoding. We start with a %, and then we give the hexadecimal value of the character that we want. So if we want to encode a hash, we encode this as a % and then a 3-5. And this is the hexadecimal value for a hash sign, so that's what the browser will interpret it as. If you want to encode a 2, you can do that with %50, because that's the ASCII key for 2, right? Some security problems that come as a result of this. URL encoding makes it sort of much harder to scan for these malicious URLs. So if I want to, as a server, block any requests that are being made to this /etc/passwd domain, I would maybe string match, and I would say, OK, is the path etc password? But if an attacker makes a request to, this big string here, this string is actually equivalent to etc password if you work out %2f becomes the slash, %65 becomes the e, and so on. But maybe our code, which is string matching, won't be able to detect this. This is known as obfuscation. We'll discuss it more in a future lecture. But one thing to note is when you're immediately looking at this, you might think, OK, why don't I just check for this string too? But what if I, as an attacker, go in and set this 65 to an e, and I leave the rest of it as URL encoded? There's an exponential number of ways to represent the same string as a result of the presence of URL encoding. OK, so I know that may be a lot kind of confusing. We just talked about a bunch of words at the same time, back to back. Let's kind of look at an example of what a simplified view of the web could look like. We see here we have a server, evanbot.com. It has a file system that has some pictures on it. It has some secrets. And then it has some of these paths that actually map to functions on a backend. So every time we one of these paths, we're just going to get the file. And if we go to one of these guys down here, we'll end up calling this backend function and actually executing it and returning the result dynamically. So we see that the browser can make a request using a URL. They can say, I want to use HTTPS, and I'm going to go to evanbot.com. then give me pictures/evanbot.jpg. So when the file system gets this request, it'll say, OK, let me go to pictures, let me go to evanbot, and then it'll return evanbot.jpg to the browser. We can also do this with like some computation. We can say the browser wants the server to draw Evan, but large. So browser sends the request to the server. The server says, OK, I have this draw endpoint. It takes in a query of bot and a query of size. And then it passes it to my backend, which runs this function and returns the result to the browser. So this is kind of a high-level way of thinking about this. This is maybe not exactly how it would be implemented in practice. But the goal with uniform resource locators, URLs, is that we can represent multiple different kinds of data from the same server using the same format of URL. The abstraction is I know who I'm talking to, I know what I want, and this file system is going to give it to us somehow. OK. Any questions so far? Yes? The COM server?
You have an address of evanbot.com.
Mm-hmm.
First, you're making requests to the .com server.
Oh, I see. So the question is, if you make a if you own evanbot.com, you're going to make a request to the .com server. Who owns that server?
You have country codes for every country.
So this is a good question.
Like .net for the non-countries.
The answer is that there is this big standards organization called ICANN, and ICANN delegates the rights to these types of things out to individual people. So there's not one .com server. There's like 20, 30 mirrors of the .com server across the world controlled by different people. And the goal is that as long as ICANN is acting as a regulating body to make sure these people are complying correctly. That is a concurrency question that is not super, consistency question that's not super in scope for this class. They do try to maintain it, and if you want to think about how, I would say probably a databases class is your best bet. Yeah. OK. So that's URLs. We'll talk about HTTP next. HTTP is the standard for how browsers communicate with web servers. It's how we're going to talk between the browsers and servers. It stands for Hypertext Transfer Protocol. That's a lot of YAP. You don't need to know that. But it's a protocol that we use to request data. But importantly, it's a request response model. So this means that we will never get a response that we haven't asked for. The browser is in control here. The browser is going to make a request, and then the server is going to answer us with a response. Or if a server needs to ask for data from someone else, the server will make a request, and it will retrieve a response. There's never a time where we're getting data unsolicited. There's this exchange that we're doing. Yeah, and there is HTTPS, which is a secured version that just uses cryptography. So it'll use certificates. It'll use public key cryptography to establish a basis. Then it'll hybrid encryption, do the whole thing. We'll learn more about this when we talk about networking, because we'll talk about the underlying protocol that makes this work. But for now, you can just kind of think about it as we have the not secure version, and then we have the version that's secured with the cryptographic primitives we talked about all throughout the last unit. OK. Parts of an HTTP request. There is a URL path that might have some query parameters. There is a method. We have two methods to choose from. Actually, there's more than two, but we'll only talk about two in this class. We have get and we have post. Get is basically asking the server for some information. It's a request that shouldn't change the server-side state. Is the request response the same thing as post get? So yeah, it's the same idea. It's yeah. OK, so if we attach a get method to a request, we're saying I want to get some information from the server. If we attach a post method to the request, it's saying I'm going to give you some data. You process this data, figure it out. Get requests should not have any data in them. Post requests can have data in them. Yeah. So other parts that are included are status codes. Or sorry, this was parts of a request, which are URL path, a method, and data. And then we'll get back a response. And in this response, we'll see a status code, which tells us what actually happened. Maybe it succeeded and we got a 200. Maybe we didn't have the right permissions and we get an access forbidden. Or maybe the thing didn't exist in the first place and we get a 404 page not found. And then we'll also get some data back, maybe a web page, audio, PDF, whatever, in response. So HTTP is not really going to regulate what data is going to get sent. It's just focused on being a protocol that lets us request data and then receive data in response. Kind of a funny blue slide. This is my favorite HTTP status code, 418. I'm a teapot. It originated from a RFC that was made for an April Fool's joke, where they were saying, I'm going to create a protocol to brew coffee with internet-connected coffee machines. And they said, if a teapot attempts to, or if a request to brew coffee is made to a teapot, it should reply with status code 418, I'm a teapot. The resulting body may be short and stout. But then, in a couple years later, the actual RFC standards people passed a standard that reserved 418 because so many people, as a result of this April Fool's joke, used it like jokingly that they didn't feel comfortable actually assigning it a value because enough people had used it like to troll. So this is not in scope, this is not important, but I think this is kind of funny. Okay, so given that, we can maybe take like a 5-ish minute break. We're at the roughly halfway mark of this presentation. Oh. Of this one, there's two. Oh, and if there's any questions, now's a good time. So we got a question over Zoom, which is, can you explain a bit more about the format of post GET requests? So really all you need to know for this class is that you will pass in a URL, you will pick a method, and if it's a GET URL, you're done. If it's a post URL, you will also include a body, and the body will have some data that is usually formatted as a string. And the server can process what it needs to and produce a response. The way these actually look, I don't have one on hand, but I can dig up an example if you'd like to see it. They're actually really simple. It's just like a string that says, I'm using HTTP, this is my path, this is my protocol, and then there's a line break, and then there's data if there's data. So for the person who was curious, this is literally what a post request looks like in terms of a string. Literally, the method you're using, it says that we're using HTTP. Here's the path, so I'm posting to just slash. It has some headers. I've only included like a content length. And then you might have some data down here at the end, which is all formatted as one big multi-line string. And this is not how you would use it in like JavaScript. We'll see an example of how that works later in the slide deck, but this is what it actually looks like when the server receives it. Okay, I think we can get started again. Where's my, there it is. Okay, so parts of a web page. we're sort of at the third bullet point we're going to talk about today. So we'll talk about HTML, we'll talk about CSS, and then we'll talk about JavaScript. We'll talk very briefly about CSS. Okay, so HTML stands for Hypertext Markup Language. It's a markup language. It lets you create documents. HTML essentially describes the structure of your page. It says, I want some text here. I want this text to be bolded. Maybe I want a table. Maybe I want an image. It tells you literally what's on your page. The way it does this is by using tags. So tags are these little things that are wrapped in angle brackets here. Here's a I tag. Each tag has a name and any number of optional properties that live within the opening of the tag here, which are name equals value pairs, and maybe some content in the middle, and then a closing bracket. Some of the tags, a very small number of them, stand alone. So here, like BR, for instance, is not closed. It's just BR, and it's a line break. But most tags get opened and closed, and we put some content in there. So like here's an example of how you would make this text bold. And HTML is hierarchical. You can kind of think of it as like a really big tree of Markdown. So tags can actually be nested, and they will like both be applied, or it'll do kind of what you expect it to do. If seeing this abstractly doesn't work for you, we'll also look at a couple of examples. Here's how to add a link in HTML. This A tag stands for anchor, because you are anchoring two pages together. And here is like, I want to place an anchor to tune.cs161.org with the message, check out these comics. And the website will look like this, where you'll have a link that lets you open that URL. We see the name of this tag is A. The property that we define is href, which stands for hypertext reference, and it refers to this URL. And then we have some content in here that actually gets this link applied to it. Another example that's a little bit more involved is constructing an HTML form. We see that at the top level here, we have a form. It takes in an action and it takes in a method. And this action tells us where the post request ends up being made. And the method tells us that we're doing a post request and not some other kind of request. And then within this form, we have individual things going on. We have some inputs. For instance, here's an input that is text, and it has a label that says name, and that will generate this name label here. So again, label for this name that says name, and then an input whose ID is name will produce something that looks like this. And then we can see a few more examples of this. We have some radio buttons, and we have a submit button. And when you press the submit button, as the form implies, based on action and feedback, it'll send a post request with this data to /feedback. So this is an example of like what you can do with HTML. And this is an example of how you can sort of nest these things to create complex layouts. And then we can also put in images. So image is another tag that doesn't have a like closing pair. It just stands alone. And it takes in a source, which is just the link to your image. And when you put this in here, first thing that happens, your browser makes the GET request to the initial server, loads the HTML. It sees that there's an image in here, and then it's going to make another HTTP GET request. And it's going to say, give me the image that lives at this URL. And then when it gets that image back, it'll plop it into the layout right there. And we'll get a website that looks like the content on the right there. So your browser, to load one page, can actually make many different HTTP requests, not just one. We can also embed entire websites. So this is not a feature that's used very often in practice, but you can do it. It's called an iframe. It stands for inner frame. So it's a frame that you place within your main frame that loads a different website. And we define the website we want to load as the source, and we give it a size. And then it'll just kind of make it happen, load the website there. question any of those things. All right. So that's kind of our HTML tour. You don't need to know too much HTML for this course, as long as you can kind of recognize that it exists with these tags, it's hierarchical in nature, and you can identify things like iframes, images, and links. You should know enough for this course. We're not going to like drill you on HTML semantics. But if you want to learn more, the Mozilla web docs are very, very good. CSS is cascading style sheets. It's a style language. It lets us determine things like what color do we want? What font do we want? How bold do we want this text to be? Do I want this box to be rounded or do I want this box to be squared off? These are all things that are defined in CSS. We will not talk about the specifics of CSS at all in this class. We might talk about later some CSS related attacks, some things you can do with CSS, but we will not talk about how to do them or how CSS works. If you want to learn that, again, MDN web docs are very, very helpful. JavaScript is our scripting language on the web. It is client-side, so it is going to run the code in your browser. This is different from when we do something like a post request and have the server do some work. This is going to happen locally on your computer. So the flow is you send out a request for a website. The website or the server grants you a request and gives you the HTML. And then in that HTML, we'll see a script tag, maybe with a link. And then you'll do another GET request, and you'll go get the script, and you'll run the script in your browser. So the script is never pertinent to the server. It's happening locally on your browser, and it's being ran and managed by your browser. We can use it to manipulate web pages, so we can control basically every element on a page, how it looks, how it interacts, what it does through JavaScript. You can embed JavaScript directly with script tags. So you can either give a link to a big JavaScript file, or you can just say script and then dump some JavaScript right in your HTML. And most modern web pages involve JavaScript. This functionality right here is happening with JavaScript. But you don't need to know too much JavaScript syntax, but we'll talk about some common stuff that you should probably recognize. So yeah, hang on. I don't like the, OK. So JavaScript fact sheet. It is a very, very high level language. It is dynamically typed. As we've said, it will coalesce a string into an integer for you when you're doing equality. It's like super easy to have bugs. It is interpreted generally. Sometimes you will see it just in time compiled if you want to speed it up, but that's not super important. You can generally think of those as the same thing. It's object-oriented, so it has full supports for classes, interfaces, etc. And JavaScript is used in almost every web application. So there's been a lot of work to make it run really, really fast. And there's been a lot of work to make it like relatively bug-free. Not the user's code, the browser's ability to run JavaScript. But I think yes, there we go. But the browser is going to be running JavaScript that any website gives you, right? So it's not like this code is guaranteed to be secure. There might be malicious JavaScript out there. But as we know, when we click onto some website, we don't expect our computer to crash and never turn on again. We expect our browser to be able to protect us from this. So the browsers are typically sandboxed to prevent anything malicious from happening. This is to say your JavaScript will run isolated from the rest of your system, and it has to make requests about your system through the browser itself. That way, like access to your main system where things can actually get messed up is delegated and can't just like happen willy-nilly. But because of the fact that you're running unchecked code, vulnerabilities in the browser's interpreter can be very, very bad. So for instance, there's an example here, just-in-time compilers. OK. So basically, this is saying if there's a use after free bug on a JavaScript object, This gives you the ability to read and write arbitrarily, which lets you break ASLR and break non-executable pages, and then you're cooked. All of this is to say JavaScript is generally memory safe, is generally sandboxed, but if there is a bug in your browser, there's nothing that's protecting you from malicious code. That's the takeaway here. Some features of JavaScript. We can modify any content on the page. So here's an example. We see here that we have a link whose ID is link. We can run this JavaScript. We can get any element with the ID link, and we can set its href attribute to some other website. And after this code runs, we see that our link went from pointing at tune.cs161.org to cs161.org/phishing. JavaScript changed the link, and now if you click it, you might go to some malicious website where something you don't want to happen happens. So this is why it's important to make sure that unintended JavaScript does not run in your website. Okay, features of JavaScript, pop-ups. Very few people ever do this with the native browser feature, but every browser supports the ability to run an alert. And an alert will just pop up on the middle of your screen with a message, and then you can press OK to dismiss it. This is very helpful when we're looking for vulnerabilities that allow us to run arbitrary JavaScript, because seeing the alert pop up on our screen is a great way to know, yeah, OK, I just ran some JavaScript without needing to know some very complicated JavaScript to test for vulnerabilities. Yeah. And then the last thing JavaScript can do is arbitrary HTTP requests. So remember earlier I said we would get to see how an HTTP request through JavaScript looks. Say we have some secret value that was provided by a server. We're not supposed to leak the secret value. If an attacker somehow gets a line like this to run, we run the fetch command. Fetch is JavaScript's HTTP request function. We tell it to send to evil.com/receive. And then we say we're going to use a post, and we attach a body that just contains our secret. This will send off our secret to evil.com, and we won't get to have control over it again. So if this is something like a secret that you need to log in, like your password or something, you might leak vulnerable data that you don't want to leak if you can run arbitrary JavaScript. And this is, in general, the syntax for doing a post request. Doing a GET request is even simpler, because you can just omit everything in the curly braces here and just end with the URL. You can also method get if you want to. There's nothing stopping you from doing that. Okay. Rendering a web page. So the way that a page actually ends up getting rendered, we start by getting our HTML from the server. We get one initial HTML document. We read through it. The server makes additional requests for any images it needs, any JavaScript it needs, other stuff that it requires. And then it parses them all. And it produces what we call a document object model, or a DOM. The DOM is basically a tree of nodes. The way it works is everything that gets rendered on the page is a node. That node has a name, which is the type of thing that it is. It has some attributes, and it has children. And if we look at any HTML, we can see the name. In this case, there are no attributes. Actually, this one also doesn't have children, so that's a bad example. Here. We look at the name. It has some attributes, and it has all of these children, right? So basically, what's going to happen is our HTML is going to get parsed into this DOM. The DOM is also going to include information from CSS about how to style the thing, how to make it look. And then we're going to execute our JavaScript and make modifications to the DOM. So the DOM itself gets changed by the JavaScript. That's what we see down here when we see document. This is referring to our DOM. And we can traverse the tree using these additional functions like getElementById. So if I say I want to get the ID that says link, I'll do a tree traversal of this DOM. I'll find the element that I need, and I'll make any changes there. And then whenever this DOM is updated, the renderer is going to kick in and it's going to re-render the part of the DOM that was changed. So basically, I have this underlying data model that represents a page, and then I have a renderer that turns that data model into the actual page itself. And then interacting with this data model causes the page to update dynamically. That's what's going on there. Okay, questions about anything I just talked about there? I know there was kind of a lot. Alrighty. In this case, we can just keep going. We'll talk about some security on the web. So, okay, that's fine. So there's a couple of risks that we take when we're using the web. The first actually has very little to do with the architecting of the web itself. This is web servers should be prevented from like being attacked, right? Like if google.com gets taken over, it's over, right? If I go to google.com/search, there's no guarantee what happens if the server that's serving us our data has been attacked by an adversary. So in this case, our goal is making sure that we're doing stuff like using memory-safe languages or not having buffer overflows in our code on our server. That way, an attacker can't take over our web server and use it for malicious purposes. This one's not super related to web, but a consequence of things being attacked is that web servers can be attacked. The next thing is that a malicious website should not be able to damage our computer. As we've already said a few times, when we open a website, we don't expect our computer to just like crash and never turn on again. It's not like when we download a program. So the way that we accomplish this is through a thing that we call sandboxing. Basically, the browser makes sure that JavaScript can't access any files on our computer. It can't access like any data it's not supposed to. And it makes sure that everything JavaScript gets to access is accessed permissively. So it'll give you a little prompt that says, do you want to let this page use your microphone, for instance, before it lets that happen. So on the other end, JavaScript is also sandboxed at a lower level. It can't access shared memory with other programs. It can't do things beyond the scope of this class, like to do side channel attacks. So we do privilege separation to make sure that our JavaScript cannot interact like a normal program with the rest of our computer, and it has to go through our browser to get access to any of the resources that it needs locally. In other words, JavaScript is meant to edit the page that you have open and nothing else, and we work very hard to make sure that it can't do anything else without your permission. Sorry, I don't know if I explained the risk very well, but if we open like a malicious website and JavaScript wasn't sandboxed, we could do something like have the JavaScript delete your system32 directory, and then it would be over. But because we have sandboxing, it couldn't do that because the browser would prevent it. Okay. Third risk is that a malicious website should not be able to tamper with other websites. If we have evil.com open and we have Gmail open in another tab, we expect that evil.com can't use JavaScript to like read our emails somehow. And the way that we do this is through same origin policy, which we'll talk about next. But the idea is basically that the browser is only going to let JavaScript run in contexts where it is supposed to run. And if it's a different website, it's going to like not allow that JavaScript to interact at all. Of course, we have to define what different means, but the general gist is JavaScript can only run on the website that's serving it. Okay, so that's some general risks. Here's the same origin policy. Same origin policy is a rule that prevents one website from tampering other unrelated websites. The browser enforces this. So again, if you have bugs in your browser or if you have a malicious browser, the same origin policy is not doing anything for you. But assuming you have a good browser, it's going to prevent malicious websites from playing around with data on other websites. The way that it works is that every website is given an origin. The origin is defined by 3 parts of the URL. It's defined by the protocol, the domain, and the port. If no port is specified, it's going to use the defaults that we said earlier, 80 for HTTP and 443 for HTTPS. And JavaScript is only allowed to run on a page if it falls in the same origin. The origin is determined by literally like string matching each of these three things. So if we look at any two websites, we can see, okay, this one's HTTP, this one's HTTPS. HTTP does not equal HTTPS, therefore there's no way this is in the same origin. Because every one of these three has to be exactly the same, like string matched. If we look at tune.cs161.org, this is not the same thing as cs161.org. They don't match literally, so this is a different origin. Likewise, if I have HTTP and there's no port on there, that's port 80. If I have port 8000 on this one, the ports aren't the same. It's not the same application. JavaScript shouldn't be able to run cross-site between these two sites. So the goal of the same origin policy is it lets our browser decide when JavaScript should be able to modify a page. And the answer is only if the JavaScript is running in the same origin. If the website that's running it matches these three things exactly. So like if I put google.com in an iframe in my website, my JavaScript cannot at all interact with google.com because the JavaScript running outside of this iframe has the origin of CS161. The JavaScript inside the iframe has the origin of Google. So these two things are distinct. So my JavaScript can't mess with google.com even if it's embedded in the same website. There are some exceptions. There are some places where we do things differently. JavaScript will always run in the origin of whatever page loads it. So if I get request from some server a JavaScript file, it's still going to run in my origin. And the sort of way to think about this is that we're going to copy paste the JavaScript from this other server, and we're going to have it run on our website. So if CS161 asks for a GET request to google.com, the JavaScript's going to come back and it's going to run in the origin of CS161, not in the origin of google.com. Another exception is that web pages can fetch and display images from other origins. It's not going to stop that from happening. But the JavaScript in the web page can only look at the image's size. It can't do things like know the content of the image or manipulate the image. It can just see, OK, there's an image here from a different origin. Here are its dimensions. That's all I've got. Finally, websites can agree to do some limited sharing where they like permissively allow stuff to happen. This is called cross-origin resource sharing. It's also the post message function in JavaScript. Neither of these are super in scope, but the important thing to know about them is basically both websites have to agree to violate same origin policy for it to happen. It can't be a one-way streak. Yeah, so that's the first lecture of the thing. We have a summary. We talked about URLs. We talked about all the different parts of a URL. And then we talked a little about URL escaping and why we need to do that and how it can be problematic for security. We talked about HTTP. We said that there is a secure version called HTTPS, and we said we'd see how it's secure later. We talked about requests having a GET or POST, having a URL, and then having some data. And we talked about a response having a status code and some data as well. And then we talked about parts of a web page. We said we have HTML for deciding what our website's content is structured as. We have CSS for deciding how our content looks. And we have JavaScript for deciding a scripting language that lets us make our website dynamic. Then we talked about the same origin policy, which basically says that two websites whose origins don't match should not interact with each other at all, unless they have the same origin, which only happens if the protocol, port, and domain match exactly, except for these exceptions in the form of JavaScript, images, and limited sharing that two parties both agree to have. OK, that's all I've got. I have any questions, and then we can do cookies, both in terms of the lecture and in terms of the cookies. OK. Yeah, so we can do maybe like a 10-minute break, and I'll set out cookies in front, and then we'll do Tanya's lecture. There are insomnia cookies. There are chocolate chip, snickerdoodle, and sugar. I also have the vegan gluten-free ones if anyone needs those. And then I know that those aren't actually good for people with celiac, so I also brought Tates. So hopefully there's something that anyone can have here.
You're muted.
Hello. Sorry about being muted. We were just doing a quick review for people on Zoom. But yeah. Yeah, so today we're gonna go over cookies and CSRF. If you are in person, I hope you enjoyed your little treat. If you're online, I hope you enjoy this photo of Evan Bot eating a cookie in spite of you not being here with us. But seventh floor and soda. You might want to go to soda 7th floor if you're here on Zoom with us if you want to participate in the cookie eating today. But anyhow, great. So yes, so cool. We're gonna go through cookies, the cookie policy, so how cookies are set, how they're sent, also how we authenticate different sessions, and then we're gonna go over this attack called CSRF, and then we're gonna talk about how to defend against it. Great. So starting with cookies. So first, let's backtrack a little and talk a little bit more about HTTP. So as we said earlier, it's a request response protocol, which means that you send exactly one request and you get exactly one response, right? So every request is kind of processed independently. And so there's no notion of like remembering a previous request or predicting a future request, right? It's kind of just like one and done. So this might be fine. And it was honestly fine on the old internet, right? Like if I'm looking at 2 images online and I have to render them, or if I want to download 2 PDFs or download 2 movies, there's kind of no reason why you need those requests to kind of be linked, right? They're all pretty separate. But maybe nowadays we might want some customized responses, right? So this isn't really going to suffice. So for example, right, if I enable dark mode on a website, if I open that website again later on, I want it to be in dark mode, right? Like I'm not expecting that to kind of be reverted, right? So we need some way of remembering this. And then also, like in the Gmail example, if I log in, right, I might want to be logged in for like some period of time. So this kind of introduces the notion of remembering some sort of state across different requests. And this is where cookies kind of get involved. Great. So all a cookie is basically just some piece of data that allows you to maintain a state across multiple requests. So we can create cookies. You know, they can be created by the server or by the browser, and it can encode some sort of state. So for example, it might contain the information about you preferring dark mode on that website. Additionally, we can store a cookie, so they're stored within the browser, and then the browser can contain this like cookie jar, which basically denotes the browser's cookie storage. And you can actually go to your settings on a browser and view your cookie jar if you want. And then also we have some notion of sending cookies, right? So in future requests that we make, we want to attach any relevant cookie, right? So the next time I make a request, the browser is going to go through my cookie jar, find all the relevant cookies, attach it to the request, and then so now we have that information. So your server is going to receive that HTTP request and then automatically get all of those attached cookies. Then the server is going to use those cookies and customize a response for you. And then, so yeah, if I have a cookie in my cookie jar that says I like dark mode, my server is going to receive an HTTP request with, if it's relevant, with the dark mode cookie attached, and then it will send you back the website in dark mode. So now it's not being forgotten. So it also basically gives this notion of connecting requests, right? Because now, since their state being preserved, requests are no longer like super independent since cookies can persist across different requests. So what exactly does a cookie look like? It's basically storing data in name value pairs, right? So you can kind of think about this as like a Python dictionary or a Java map. So all of the data that you want is like in this like name value pair. In this visual, right? The name of our cookie is called theme and the value is dark. So in this example, this is how our dark mode cookie might look. There's also a lot of other stuff in this gigantic chart, right? So yeah, we have a domain attribute and a path attribute, and this is kind of related to the question of cookies being relevant, right? So the domain and path are going to help us kind of figure that out a little bit. So yeah, here basically we're saying, well, where do we want dark mode enabled, right? I want dark mode enabled on tune.cs161.org/exorcist, right? So yeah, this is basically telling us some notion of relevance, and we'll go through it a little bit more because it's not that straightforward, but it gives some information. So you can kind of think about it as like the domain and path of where you want this cookie to like kind of apply. We also have some security attributes. So yeah, if the secure flag is set to true, then we're only going to send this cookie over an HTTPS protocol and not HTTP. So if our URL that we're like, visiting is HTTP, we're not going to send our cookie if it has a secure flag set to be true. We also had this like HTTP only flag, and it's honestly like a very strange name for what this actually means. But basically, all it's saying is if HTTP only is true, we will not allow JavaScript to access the cookie, right? So if that's false, JavaScript is actually allowed to reach into your browser's cookie jar and then access cookies, modify them, and then create them even, right? So we can set this to be false to say we don't want this cookie to be a part of that, right? And this can happen because if you recall, cookies are stored in your browser and JavaScript also runs on the browser. Now, lastly, we have the expires attribute, which if you maybe can predict, tells you when the cookie expires, right? So it's kind of like this timestamp that we have over here, and it basically tells you when the cookie is no longer relevant. So it's like this like timestamp thing. When a cookie expires, it is deleted from your cookie jar and it just no longer is involved in like your life, like it's done. So for example, right, in like logins, I might not want to be logged in for like the end of time, right? Like at some point I might want to be logged out, and then so the way that we can do that is we can say, okay, like we have this like login cookie, right? And we'll talk about that more later, it's important. But we might have this like login cookie, and then it will expire kind of in a week, and then the cookie is like gone, and then we have to like re-get it somehow when we log in. So we're going to move on to cookie policy. Was that all clear for everybody? Cool, amazing. So now we're going to talk about cookie policy. Okay, so previously, we kind of went over the following. First, servers can create cookies. So when you make an HTTP request, in the server's response, they can include a cookie and be like, hey, put this in your cookie jar, and then the next time you make a request, if that cookie matters, like attach it on your next relevant request, right? If we stop there, and that's all that we like set up, there's a lot of issues with that. So first and foremost, right, I want my server to only be able to set cookies for related websites, right? So if I have this website called evil.com, should evil.com be allowed to make cookies for google.com? So like maybe evil.com sends you a cookie saying, oh, let's keep, like they set the domain to be google.com and be like, oh, let's keep google.com in dark mode, right? But that doesn't make any sense because evil and Google are like not related at all. So we're not gonna want to be allowing this. So we need some notion of kind of like controlling access on that front. And also browsers need to send the cookies to the right places, right? So a cookie could contain sensitive values. When we were talking about logging in, right, that could contain some sort of like sensitive credentials. And so if I am logging into Google, but somehow I send that cookie with my credentials to evil.com, well, now evil.com knows all of your private information about Google, which would kind of suck. So we want to keep those things like separate. So you can kind of draw connections with something we talked about earlier called the same origin policy. However, this is not the same thing, but it's kind of like a same notion of basically being like, you want things on the same website to work with each other in a general sense and have separated like websites not interact. That's basically the main thing. So unrelated things should not be able to preserve state for like completely unrelated things. Okay, so now let's define these rules in this formal setting called the cookie policy. So first, note that the cookie policy is enforced by the browser because cookies are stored and managed on the browser side. So this is going to help address some of the things that I just talked about, right? So the question, right, is if someone hands us a cookie, should I keep this cookie and put it in my cookie jar, or should I throw it away, right? So going back to our example with Evil and Google, we need to figure out when Evil is sending us information that's about Google, and then know that when Evil is sending us information about something unrelated, to throw that away. And then also, if we're trying to make a request to the server, well, should I attach cookie, this new cookie, or should I not attach it, right? So that's what a cookie policy is going to answer for us. And cookie policies are specific to cookies and it's not the same origin policy. Like cookie policies are for cookies and same origin policy is not for cookies, right? So both can relate to ensuring some sort of separation between different websites. However, one is for the interaction of two different tabs, and one of them is about sending and receiving cookies. So they're not the same thing. So before we dive any deeper, we're going to talk about domains because this is important when we're like defining who can control what. Okay, great. So the first thing that you might be seeing is that there's, in like a lot of the links that we're showing you, there's a lot of dots, right? Like we had like tune.cs161.org, right? So what do the dots actually mean? Well, you can kind of view this as establishing some sort of hierarchy, right? So we have this little tree hierarchy thing for you. And basically, you can kind of see that we have .edu, and below .edu, it's berkeley.edu and mit.edu, right? And above .edu is like the root, right? So as we can see, Berkeley and MIT are below this like .edu thing. And then similarly, we have CS161.org and edstem.org under this .org. So it's like kind of like a hierarchy, right? So if I had like tune.cs161.org and fall25.cs161.org, they're going to fall under that bad boy, right? The cs161.org thing, right? So this is kind of how our hierarchy is being established. So more vocabulary terms here. This is an example of like one branch of the tree that I showed you on the previous slide. And we have this thing called the top level domain. And that is basically something that is directly below the root of the tree. So it's just like a dot and then like some letters, right? So .edu is a top level domain. Then we have subdomains, right? So eeks.berkeley.edu is a subdomain of berkeley.edu. You can see that it is below it on the tree. So this is like kind of how our hierarchy is established. Okay, so this is kind of like a lot, and this is kind of how our policy is set up. So I'll probably pause for questions after this one. But yes, so we will now use the domain hierarchy that I just talked about to establish whether or not our browser is going to accept a cookie or throw it away. So we are going to answer this by taking the domain of the server, which is basically the server that is sending you a response. We're going to call that X, okay? And the domain attribute of the cookie, we're going to call that Y. All right, so for example, when evil.com was sending us a cookie to make google.com always be set in dark mode, evil.com is going to be like X because that is the server sending us the cookie, right? That's the thing sending us a response. We're going to call that X. And then google.com is Y because that is the domain attribute specified in the cookie. All right, so we want the domain attribute, or Y, to be a domain suffix of the server's domain, or X, right? So what the heck does domain suffix mean? Well, we can kind of word it in three equivalent ways. First, X ends in Y, right? So if we have a domain and the domain suffix is like Y, we're basically saying that X ends in Y, right? X is below or equal to Y on that big hierarchy that we showed you earlier. And then lastly, X is kind of like more specific than Y, right? So for example, because it's a lot of hand waving, let's look at mail.google.com, okay? So mail.google.com should be allowed to set cookies for google.com because google.com is a domain suffix of mail.google.com. Equivalently, we can say that it is true because mail.google.com is more specific than google.com, or that mail.google.com ends in google.com, etc., right? So that's like rule number one. And then rule number two is that we do not want websites to be setting cookies for top level domains, right? So if I let google.com set a cookie for .com, that affects so many websites. So we want to stop that from happening as well. So that was a lot of .coms, suffixes, X and Ys. Do we have any questions on that? Or does this make sense? Does this make sense to people? Okay, I'm going to keep going. But yes, this is the rule. Okay, well now what about sending cookies? So let's kind of figure out where to send cookies and like define this like notion of relevance, right? So we can compare the domain attribute and the path attribute of the cookie to the server's domain and path. Okay, so in specific, we want the domain attribute of the cookie to be a domain suffix of the server's domain, and then we want the path attribute of the cookie to be a prefix of the server's path, right? So intuitively, the way that we can look at this is, okay, when a cookie has a domain attribute for google.com, we can kind of see this cookie as being relevant for anything ending in google.com. So servers set cookies for like more general websites. So mail.google.com sets stuff for like google.com. And then we can only send cookies to servers if the cookie is like more general, right? So a cookie with the domain attribute google.com can get sent back to like mail.google.com in this case, because the domain attribute google.com is a domain suffix of the server, which is mail.google.com. Another way of making this kind of easier for people is this cool, handy little trick about whether or not we should send a cookie to a URL. So this is like some steps that you can do if you ever have to figure this out yourself. First, let's right align the domains. So as you can see here, we have like right aligned cs161.org with to.cs161.org. So we can see that the domain is a suffix of the server's domain. Now let's left align the paths, right? So here we kind of like set up the slashes to align with each other after the domain. And as we can see that the word cryptoverse is like the prefix of like the path, okay? So we can kind of see that these match like identically. So when you concatenate these and put these together and you line them up, as we said earlier, we can kind of see that, okay, well, they match, right? That's good. So if the domain and paths all match, then we can send the cookie, yay, woohoo, so we can send this. However, we can't send this, right? Because the cookie's path is not a prefix of the server's path. So as you can see, because there's a difference, we can no longer send these cookies. So if it ever gets confusing about sending cookies, do this like alignment and it will help you out. It's a little trick. So yeah, here we can see that the cookie will not be sent in this case because they don't match. So, okay, question for the audience. Do we think that this cookie will be sent to the server? Raise your hand if you think, yes, this cookie will be sent. Raise your hand if you think, no, this cookie will not be sent. I see someone raising their hand for no, and that will be correct because as you can see here, summer24.cs161.org does not match www.cs161.org. Okay, yeah, so amazing. Do we have any questions on that? Cool. So now I'm going to talk about this out of scope thing that personally I think is a little bit complicated. And yeah, we're gonna do our best. If it's confusing, don't worry about it because it's out of scope, but it is pretty cool. So basically, it is possible to do some attacks on cookies, and this is because there can be some ambiguity when sending cookies, right? So for example, if you send two cookies at like the exact same time with like the same page, or like to a same page with the same name, like cookie name, it's kind of like they're sent in this like undefined order, and it can be difficult to distinguish them. So let's take a look at these two cookies. It has this name, it has the domain, it has the path, right? And then here's another cookie. And on first glance, it might look different, but we can see that it's like the same name, two different values, the same domain, and two different paths. But basically, if I'm opening bank.com/page, both of these cookies get sent in like this undefined order. So we don't know which one gets received first. And the server themselves doesn't have access to this like domain and path attribute. So you're kind of getting two cookies that seem to say the same thing, but they have two different values. So you're like, okay, well, like, what the heck? What do I do? So the server's not really able to tell these cookies apart, and that's not good. So this is going to kind of talk a little bit about like 162 related stuff with processes, and apparently like 152, but I've never taken that. So yeah, if you understand, like, if you haven't taken those courses, like, don't stress, no pressure. We can always talk after lecture. That rhymed. Okay, so basically, in this original browser design, you have your tabs, and each tab kind of runs in its own process, right? So this can be pretty beneficial. So first of all, processes are pretty much isolated because of your operating system, so they're not going to be able to access other processes. And what this does is it makes attacks like pretty much harder because you actually have to exploit like browser code and escape the sandbox somehow in order to like perform some sort of attack because of like this isolation. And additionally, because everything's isolated, if one tab crashes, it's just like one process that crashes, your entire browser is not going to go. So this seems pretty cool. However, there are some problems, right? So you might have a scenario where you want to keep two things isolated that are in the same tab. So the most notable example of this is if one website opens up an iframe and then that has content from like another website, right? Since they're coming from two different origins, we want them to be separate, but because they're sharing a process because they're on the same tab, they're not really isolated in the way that two different tabs are. And so, yeah, basically JavaScript from like one origin, same origin policy is going to help us here, but the fact that they're sharing a process is a problem, is basically what the thing is here. So we can exploit this. And basically, we're going to do this called the Spectre attack, and the Spectre is like an attack exploiting this specific browser design, right? So the way that it's structured is the victim is going to visit evil.com in a browser tab. Then evil.com is going to open an iframe with a victim.com, right? So with the same origin policy, JavaScript from evil.com should not be able to read cookies from victim.com. But the one thing to remember is evil and victim are now running on the same process. They're like sharing a process. And basically, there's no more like operating system sandboxing anymore, and only the JavaScript compiler is like adding some isolation here. So if we're able to somehow break this, we can read memory from victim.com. So how do we actually now exploit this like processor, right? So basically, modern processors are pretty much, I'm gonna like go through this quickly, but basically they're supposed to be really, really fast, right? Like that's the goal. And so they're going to use this thing called branch prediction and speculative execution, right? So essentially here, we don't want to keep people waiting for too long, right? So it's more optimized to somehow kind of guess what's going to go down in the code and then start executing it. And then when we need the result, we can just give you the result, right? So the drawback is that if you're making a prediction is not always correct. So the way that this works is like usually you have all the work done, but you don't fully commit it. So you don't put it in like the register until like you know that it's what's actually happened. So yeah, as long as you don't write to a register, okay, well, nothing actually happened. You didn't do anything wrong, right? But Spectre, you can actually take advantage of the fact that there is like this work being done that might not necessarily be what the program is intending to do. And you can use like side channels, for example, like timing or like the state of the cache to kind of detect when speculative execution has done something wrong and what the input to that like wrong execution kind of was. Then what you're able to do is you're kind of able to force speculative execution to be wrong by making like, you can kind of force wrong predictions in that way, right? So normally speaking, this isn't really like a problem because you're not really writing to the register. But if you're doing something that includes a memory load, then the memory is going to be loaded into the cache, which is going to leak some information and like disrupt the cache, right? So you're kind of able to access information that you weren't supposed to just because of the way the optimization is occurring. So here's a cool example. This is like some code. So it's a while loop, right? If I is less than or equal to 1,000, we're going to keep doing legal stuff. If I is greater than 1,000, we're going to do some illegal things, and we're going to increment I every time, right? This is our code. Basically, what we're going to do is we're going to kind of like use side channels to break the JavaScript, to break the memory isolation, right? So let's kind of go back through like what's going on here. So in this example, evil.com kind of has an iframe loaded with victim.com inside. Now let's say that like evil.com is like going through this while loop, and it's going to keep doing like legitimate instructions for like a long time, right? Because I is 0, it's going up to 1,000. So it's going to keep doing these like legitimate instructions. And then basically, yeah, so it's going to keep doing like what it's supposed to do. And the branch predictor is eventually going to be like, okay, well, it's happened like 999 times. I've been doing this like exact same like set of like legal instructions. So you would assume after 999 times that we're probably going to keep doing some legal stuff. And this is going to be correct until like that last, oh my God, until that last loop iteration, right? So in the regular runs that we're going to have, I is going to keep increasing, but in the speculative run, right, we're going to assume that the while loop is going to run again, right? But I is going to be on the last, like, in that first illegal iteration that's not supposed to happen, I is going to be greater than 1,000, right? Because that's the first time that the while loop's not supposed to run, right? So now we're going to run this like illegal thing, right, in our speculative execution. So yeah, on the last run of the loop, the processor is going to incorrectly guess that the program's going to keep going and start running the loop one more time. And then we're going to do this like illegal computation, right? Maybe, for example, we're trying to like access some cookies that we're not supposed to access, right? Now, if that is like loaded into a cache or there's some other side channel where we're able to access that information because they're sharing a process, then that information is now getting leaked, right? So if you do this with a lot of different illegal things, eventually you can leak all of the illegal stuff that you want. So that is basically the lore behind what I think is a pretty complicated attack that is out of scope. So now how do we defend against this? Well, now everything kind of runs based on origin. So each origin runs in its own process, not each tab running in its own process. So it's a little more granular now, and this is called site isolation. And basically now, so the operating system is going to, you know that the operating system is going to prevent different processes from interacting. So if we have each like origin running in its own process, now different origins cannot access each other at the OS level. Now we defeat the Spectre attack because they're no longer, like two different origins will no longer be sharing a process in any case. So both the evil.com frame, the evil.com is going to be running in one process, and the victim.com frame will be running in another process. So it's like isolated now. So yep, speculative execution. Like this attack is basically no longer going to work because the memory can no longer, it's like completely isolated memory, which is like what we want. So now you would have to break OS isolation to perform this attack, which is substantially harder than what we did in Spectre. But now there's a cost, right? Processes are pretty expensive. And if I like, there's a lot of memory overhead now when loading a website, right? If I have a photo, like a website with like 5 different images, and each image comes from a different origin, that's like 5 processes, which is like a lot of overhead. So can be pretty expensive and a lot of expensive context switching. So yeah, takeaways here is that enforcing isolation basically requires a secure browser design, and it can be hard to get that right. And then also the web was not designed with security in mind, and that's why a lot of defenses were added afterwards. So that's why the internet's a little awkward, right? Like we have all these policies and all these things, and this is pretty much why, right? Like we didn't think about it, we just kind of made it. So now back to the in-scope stuff. We're going to talk about session authentication. Are we feeling like we need a break, or are we feeling like we can keep going? Okay, we're going to keep going. Thank you. Oh my God, this cookie's good. Okay, great. So that was basically all you need to know about the base cookie knowledge. So yeah, cool. We now know how to make cookies for like dark mode and requests, right? But let's talk about another common use case, which is kind of like logging in. So we have this notion of a session, and basically what a session is it's a sequence of like requests and responses that we want to be associated with the same user, right? So if I log into Gmail, I might want to send emails and I might want to read emails. And these are all like separate requests, but they're all coming from me. Like I'm reading my emails, I'm sending emails to somebody from me, right? So this is like kind of like in a session. Now, if I like log out, I kind of like, I want the session to end at some point. Like I want to log out, and I might want to like, you know, if I haven't opened my Gmail in a month, like I would hope I've been logged out by that point, right? So yeah, how do we actually implement a session? Naively, we can have the user log in every single time they want to make a request. But if you think about that, that's horrible because every single time I open an email, I have to log in. If I want to send an email, I have to log in. If I want to like draft an email, gotta log in, right? That's all traumatizing and we don't want to do that. So this can be extremely inconvenient. So perhaps there's a way that the browser can automatically store some information and like preserve state. Hint, hint, we can use cookies somehow, right? So we're going to use cookies as a method of achieving our goal of providing some like sessions and session authentication. So just to reiterate, cookies have all sorts of use cases, right? It's like general, right? We're talking about like dark mode, that was like the example I was using. That's the only one that's coming to mind. But you have a lot of use cases for cookies to preserve some sort of state, and session authentication is just one of those use cases. Okay, great. So this is a really helpful example of how you might want to think about sessions and session authentication. So yeah, let's say I'm going to a concert. Hopefully people have been to one. It's really fun. But I have a ticket and I have my ID, right? And I have a door person who I'm going to show my ticket and my ID to, right? And if they validate my credentials, right? Like I have a real ticket, I look like how I look in my ID, they're going to give me a wristband, right? Because like I'm good to go for the concert. But let's say like I left like my water bottle in my car and it's really hot in there. So I might want to leave the venue, go get my water bottle and come back. And it might be a little bit annoying if I had to pull out my ID, pull out my ticket again and show them. But if I have that wristband, I can just show them like, hey, I already like entered the venue before, here's my wristband, and then they might let me back in. So it's a good way of kind of like thinking about it. One drawback of the analogy is that like you kind of want the wristband to look different for each person because they want to know like who specifically you are, but in general, it's a pretty good way to think about it. So similarly, we kind of have this thing called a session token, which is a secret value that is going to associate requests with a specific user, right? In this case, the session token is kind of like your wristband at the concert. So on your first visit to your website, you can present the username, which is like the ticket, the password, which is like your ID. You show them to the website and the server, and you're going to get your session token or your wristband, right? So you get your session token after logging in. Now, so the server is basically going to generate and send you a session token, and then it's going to tell you to store it, right? So that's kind of like the venue giving you your wristband. So now we have to remember our session token, right? Because otherwise that kind of defeats the purpose. And the browser is going to have to remember like everybody's session token over all of the logins. So there's some database for this where they're remembering everybody, and you just have to remember your own. So if I'm making subsequent requests to the server, I'm going to want to attach my second session token to every single request that I'm making. Then the server is going to check for the session token and allow that request to be associated with you without requiring you to re-log in. So yay, that's a cool win. We can kind of implement session tokens with cookies. So just to reiterate, session tokens and cookies are not the same thing. The goal is having a session token, and we are going to achieve the having of a session token by using a cookie, right? So the cookie is like the means by which we will have a session token, right? So a session token is a high-level idea, and we're going to use cookies to implement it. So if I visit, if I visit a website for the first time, I'm going to kind of make a request to log in. If my login credentials are valid, I'm going to get a session token. With future requests that I make, the browser is going to attach my session token cookie, because we're using cookies for this. It's going to attach it to my request, right? Because like as we talked about earlier, cookies kind of get attached to anything that they're relevant for. So my session token cookie might be attached to like my Gmail requests if that's like what I'm using, right? So the server is going to identify who I am with that session token cookie, right? So on my emails, if I send someone an email, the server is going to receive my request and also my session token cookie, look at my cookie and be like, oh, well, that's Tanya, right? So that's kind of what's happening. And that allows you to bypass having to enter your username and password every single time. So when you log out or your session times out, your session token cookie just gets deleted from the cookie jar. All right, so pretty chill, pretty fun. If anyone has questions, like hand up, but I think that, yeah, hopefully that made sense. Okay, cool. So one thing that I haven't called out yet is that the session token really needs to be some like random unique value as like your session ID, right? So in your cookie, right, you have your name and like your value attribute. And so the name might be like session ID or whatever, and the value needs to be something random, right? So the browser is going to remember the domain of the server to like send that cookie to, and is going to send that value along every single request that we make to that domain. And the server is going to remember the association between that session ID and like who you are, right? So it's like different things like you have to remember, right? You need to remember, browser needs to remember, I guess like when to send that cookie, and the server needs to remember when I receive that cookie, who do I associate this person with? So there's infrastructure for that. Okay, yeah. So there obviously needs to be a lot of security when it comes to logging in, right? So here are some considerations. First, we want our session tokens to be secret, because if it gets stolen by an attacker, well then now I can just log in and pretend to be you, because if I have that right value in my session token, I can just say that I'm you, right? So if a request has your session token attached, the server is going to look at that request and think that it came from you. So yes, we need to keep them secret. We also want the servers to protect session tokens in terms of like how they're generated, right? So if I like use a timestamp as my session token, well, someone might be able to guess somebody's session token and like impersonate somebody else. So we need it to be like a random scheme, right? So you can kind of think about this as like almost generating a key in cryptography. Like it really does need to be like something you cannot guess. One example of this is we can use a pseudo random number generator to generate a session token that way, and that way people really will not be able to have like a easy time guessing. All right. So yeah, we also want the browser to enforce isolation so that one tab cannot steal a session token from like another tab. And so yeah, our cookie policy is going to prevent evil.com, for example, from seeing session token cookies from google.com, because we talked about that with the cookie policy, right? The domain doesn't match. And then same origin policy is going to prevent different websites from accessing like values in other tabs. So yes, we need those things enforced. And then lastly, we want to send the session tokens to like the right people, which is super important. And we have our cookie policy that allows this to happen, right? So we have a lot of infrastructure that's going to help us, and we're going to add a little bit more so that everything's secure. But yes. So, well, how do we kind of like generate a session token cookie? Like what attributes should we make? The answer is basically it's like generally up to you, right? So we can see all of the fields that we talked about earlier. We have our name as like this token or like ID or whatever, and the value is this like truly random value there. We have our domain and path, which is basically telling us like where do we want to send this cookie to, right? But well, I mean, do I want being logged into Gmail to also mean that I'm logged into Google Maps? If that's the case, then really we want this to be like google.com instead of mail.google.com, right? We can like make things a little bit more general. But maybe we don't want that, right? We can also set like specific paths and whatnot. And then we also have like the secure flag, right? That's probably the only one that you maybe want to set as true, because, well, I mean, I don't want to send my like login credentials over like this like insecure channel where people can steal it. So maybe, yeah, you want that set to be true. Well, HTTP only, do I want JavaScript to jump into my cookie jar, grab my session token cookie, and like change it? Maybe you want that, maybe you don't. And then the expiration time, like how long do we want people to be like logged in for? So these are all like customizable, but things to consider when you're handling things like people's credentials. Okay, now we're going to talk about what's wrong with this and how we can attack it. Yeah, great. So session tokens are basically, as a review, to associate a request with a specific user. And browsers are going to automatically attach relevant cookies in every single request that you make. So these are two things to keep in mind when we talk about what's wrong with this. Okay, great. So here's an idea. So what if the attacker is going to trick the victim into making an unintended request that they did not mean to do, right? So if that happens, well, the browser is just going to send a request and automatically attach all relevant cookies to that request, even if you didn't mean to do it, right? So basically, the server is just going to think, oh, well, Tanya made a request to transfer $1,000 to Jonah, even if I didn't mean to do that, right? And my token's going to be attached to it because the browser just automatically attaches all the relevant cookies. So they're going to think that it was me when it really wasn't. And this is basically going to be a problem just because of the automatic like attachment that goes down. So it's going to look like it's coming from you. Here's an example, like a big analogy, right? So let's say that I have $1,000 in my bank account. And if I want to pay somebody money, I can do this by writing them a check. And then, so let's say I write a check to pay Alice $50. That means I want to send Alice $50. So now let's say I'm like chilling and vibing and hanging out at a party, and this stranger named Genevieve comes up to me and asks me to pass like a love note to somebody. And they're like, oh, don't read it, but just like, can you send it to like Bill, right? So I'm like, okay, like out of respect for Genevieve, I'm going to send this note to Bill, but I'm not going to read it to like respect her privacy, right? But if that note is actually a check that is saying, go give Genevieve $1,000, and I like give it to my banker, who might be Bill, right? Then the banker is just going to take that check, see that it's, oh, well, clearly like Tanya has given me a check to pay Genevieve $1,000. even if I didn't mean to do that because I didn't read the note, they're obviously just going to be like, oh, okay, like that's what they assumed, right? Like, how could I make that mistake? So they're just going to assume that you meant to do it, even if you didn't. So that's kind of the same thing that happens on the internet. And here is a visual example of what this attack looks like. So first, let's have the user log in. So the user is going to get a cookie with their session token in it and put the cookie in their cookie jar. So now if the user and the server want to talk, that cookie with their like session token and stuff is going to be attached to all of the requests that they're making, as long as they see that cookie there. Well, now let's have the attacker trick the user into making some sort of malicious request. So in the same way of tricking me into giving Genevieve $1,000, maybe we're making them do that online pretty much. So then now, if the user executes that request, the server has no way of like knowing what the user's intention actually was, right? The cookie just automatically gets attached, the user's automatically logged in, the request automatically goes through because there's no way of like establishing intent here. So this is basically abusing the fact that cookies are automatically attached to the requests. You don't get to ask to send specific cookies. It's based on the cookie policy. And this is going to automatically authorize like the request that you're making. But then obviously this is like a little weird, right? Like how are we actually going to trick somebody online into doing a malicious request to a server, right? Like that's obviously the crux. Because everything else has just been like, oh, you're going to trick them and then we can't establish intent. But like, how do we actually trick them? There's actually a lot of different ways. Okay, so maybe we can trick the victim into clicking a link, right? So the attacker can send a user a link that might be like something that's pretty enticing over email, right? So they get the link, the user clicks on the link, and maybe that link is actually a GET request to pay somebody $100, and like maybe that's what runs, right? So I don't know if you ever get like spam emails, like maybe that's what's going on, right? So there are other ways that you can get a user to click a malicious link. Maybe the link leads you to an attacker's website, and the website runs some JavaScript that like executes requests that get you to pay people or do something else unintended. So yeah, having the user visit a malicious website and like the second strategy of putting HTML on a website that the victim will visit, it's a little bit more difficult. But maybe if you want to like embed images in that website, you can use image tags, link a URL in this case, right? That like transfers $100 to Mallory, right? So yeah, and then when the browser tries to load that image, it's going to do a GET request at this link, which is actually going to execute the transferring of money to Mallory, and that's what's going to run. So yeah, that is kind of what's going on here. So getting like a post request to run is a little bit more difficult. So recall that post requests can kind of like change the state of the server, right? You're adding things there, but GET requests don't really do that. Oh yes. Because basically the SRC link, what it does is it runs a GET request to whatever that link says to like get the image. Yeah. So you're basically like running that to get it. That's a good question though. And honestly, like I was super confused about that too, but that's why. Okay, great. But yeah, that's what happens there. And now how do we get it to execute a post request? That's a little bit harder, right? Because we're changing server state. And GET requests don't really do that. So links are usually like GET requests, right? Because you're trying to get information from somewhere or like get a website, get an image, etc., right? But that's not really what a post request does. So we need to be a little bit more malicious. Basically, one way that we can do this is we can trick the user into clicking on a link that opens an attacker's website. But then maybe the website itself has some JavaScript that runs a post request. We can also put some JavaScript on a website a user visits often, right? So like maybe they're on some sort of like some forum or whatever. And then it just needs to be a page where you can control like and put your JavaScript on there, right? So when a user visits that website now, the JavaScript is going to execute, and thus you've made them run a request that they did not intend to make. You can also even like, I think it's like mal-advertising. We talk about this a little bit later in the lecture, but you can buy advertisements that are like malicious and put JavaScript in there even, right? So there's a lot of different ways to do this. You can kind of, again, trick them into clicking some sort of link to a website that runs JavaScript or put your JavaScript on a website that they visit frequently. Okay, this is really cool. These are the top 25 most dangerous software weaknesses. CSRF is number 9, right? So this is still like actually like a pretty big issue as of 2020. And you can kind of like go through this, but most of our web attacks are going to be on here. So yeah, or a lot of our web attacks are going to check some of these off. So pretty cool. This is relevant. Briefly kind of going over this, in the real world, if you have like a smart fridge or like a smart like light bulb, I don't really know what they have. There's a lot of like smart devices. A lot of times they have a very like default login URL, right? Something that looks like this. As you can see, username is admin and this like top link, password is admin, right? If you trick the user into clicking on a link like the ones that we have above, you can kind of like trick the user into logging in or making requests. And basically the reason that this works is because they just have like username admin, password admin. And if you click on it, it might work, right? The credentials could be correct. So yeah, things might just, basically what this is saying is that it's defaulted, and we're going to talk about CSRF defenses, and they're not really implemented here. So this is like an example in the real world. And another example is like, that was the word, malvertising, right? People can put in malicious advertisements on websites. So maybe like I'm gonna buy this like this space to like advertise something. Even if it's like maybe on a legitimate website, we can still have some malicious code like JavaScript that runs and cause them to execute requests that they didn't intend to do because our advertisement was the problem. So this actually happened a very long time ago. This is like 2008. So when I was 4, there was a CSRF vulnerability on YouTube. And basically you can kind of like, you could trick the user into like making like one single request. And then if you're able to do that, you could then trick them into sharing videos that they didn't mean to, subscribing to channels they didn't mean to, adding videos to playlists, or just like making malicious things happen that they did not intend to do. So you can have them do a variety of different things. So yeah, it actually happened in the real world. And it also happened on Facebook too. If you guys are interested, you should look this up because it is pretty cool. But it goes to show that this is something that actually has happened, especially back in the day, like 2008, 2009. But it has happened back in the day, and it is not uncommon. So yes, it's kind of cool. Now we're going to talk about CSRF defenses. All right. So essentially, if you kind of like send a request with the right cookie, there's nothing that really stops the request from going through. It's just going to look at that cookie, be like, okay, cool, and then run your request. So we need to add some sort of extra security that's beyond just the session token value that we have, right? So we're going to go over CSRF tokens and same-site cookie attributes, and we'll talk about that. Okay, great. So the problem with CSRF is that we're basically just tricking the user into doing something that they didn't intend to do. And the only reason that this works in the first place is because cookies are automatically attached, or you're like automatically attaching the cookie every single time, right? You don't really say, oh, please don't, like kind of just happens. So when an attacker kind of crafts a malicious request, we kind of didn't need a lot of information to make that request, right? So like in our bank balance example, it was just like, oh, well, send $100 amount to recipient Genevieve, right? It's pretty easy to make, like that link. And so if I generate a request and a stranger generates a request, there's really no way to distinguish like which one was mine and which one was the stranger's because they're so easy to forge. There was like 2 parameters, right? So yeah, our goal here now is to make it a little bit harder to distinguish between legitimate and illegitimate requests. And we can do this by adding another secret value that the attacker will not know. So going back to the bank analogy, let's say that the bank now only accepts checks that have the sender's like birthday on it, right? So, well, now a random attacker who's trying to send the check to the bank and like impersonate me is going to have to know my birthday. But like they don't know my birthday if they're just like random, hopefully, right? In real world, maybe it's like your social security number, which they definitely don't know, God willing. So yeah. Yeah, great. So a CSRF token is basically like kind of this secret value that you have, kind of like the birthday that we're asking you to write on your check. And it's a secret value that you put in a request in order for the request to be validated. So a legitimate request can be like identified because if we're going to call that like value, by the way, the CSRF token, right? So it's like this like secret value that only you know that we're going to validate, right? And basically we can distinguish now between legitimate and illegitimate requests because the legitimate request is going to know the CSRF token, and the attacker can't just really forge a request with like the URL because they're not going to know what the CSRF token is. All right, so now where do we put this? Raise your hand if you think it's a good idea to put this value in the cookie. It is, yes. I see some like shaking of heads. This is a bad idea to put it in the cookie. Do not do this because that would basically be pointless since all of the cookies are just automatically attached to any requests. So remember, the CSRF token is going to be separate from the cookie and not attached to the cookie because, well, that would defeat the purpose. So we need some way of like attaching it that is not putting it in the cookie. So for example, maybe let's add it as an argument to our get URLs, right? So in our bank example, maybe we say money, say like we want to transfer $1,000 to Mallory and our CSRF token is equal to this, right? So, well, now the attacker isn't going to know how to craft the malicious URL without knowing the CSRF token. Great. So we can, because earlier we were kind of talking like CSRF attacks can happen even when you're filling out a form, right? So if I visit an attacker's page, what I can do is I can write a JavaScript function that when I open this website, it automatically fills out this form with all these fields like maliciously filled out, and then I put a post request with all the values in that form, and like that would be pretty bad. So now that can be stopped with the CSRF token because a request will not just be submitted, we also need the CSRF token in that request to be valid. So now we can maybe add an extra field in that form that says what is your CSRF token, and then it has to match when you make that request. Attackers, right, like can't just put in their own token because everyone's going to have a different CSRF token, so that validation is no longer going to work. So yes, nowadays modern browsers and servers are going to like pre-fill the CSRF token for you, which is why you don't necessarily see it yourself. Everyone get home safe. It's like really going down out there. But yeah, okay, great. So this is like a visual example. So a user is going to log in and get a top secret CSRF token, right? So here they're going to get their session token and then they're going to get their like CSRF token, right? So you get both of them. Now maybe let's have this attacker kind of say, okay, make this request with like some token, right? Maybe they try to put in their token or something like that. But when we make the request, the token is going to be the attacker's token and not my token. So then they're going to compare the tokens are going to be wrong, and then the request is going to fail. Yikes. Okay, great. So because the attacker doesn't know the token, like your token, it's no longer going to work. That's our first defense. Do we have any questions on the first defense? Yes. Is it stored in the browser? Yes. Oh, refer header? Okay.
Why is it not blocked by,
Why is it not what?
blocked by ports? URL.
Oh. Yeah, can you get the door? Why is it not blocked? Honestly, like, do you know that, Jonah? Why is the request not blocked by course? Wait, which request?
Well, you're making the request to be hacked, but
Yes.
you're getting none of ports that you're defining.
Like, are you talking about the example where I opened the form? And like,
But answer my. I'll add.
okay, yeah, we can also meet after lecture and go over that. Anyhow, the other defense that we have is the refer header. So, yes, in a CSRF attack, the victim's request is kind of coming from like this malicious website, right? So, if I'm like hitting the button to subscribe to a YouTube channel, then my request to subscribe to the YouTube channel is coming from youtube.com, right? That's a legitimate request. If evil.com is trying to make me subscribe to youtube.com, then like that's the like place where my request is coming from is going to be like evil.com. All right. So maybe let's try to figure out like where a request is actually coming from, right? So you have this thing called a refer header, which tells you where a request is originating from, right? So if I am on Facebook and I type in my username and password, the refer head is going to tell me that my like login request is coming from facebook.com. If some image tag on a forum forces me to make a request, then the refer header is going to contain the URL of the forum and not facebook.com. So if I'm on like a website and I have that website run some JavaScript to make a request, then the refer header is going to be like, it's going to basically say that the request occurred when they were on the attacker's website and not when they were on the website that they meant. So basically, yeah. So yeah, CSRF attack, the victim usually makes the request from a different website. And we have this thing called a refer header, which basically tells us which web page the request came from. You might be wondering why it is like spelled with one R and not two R's. It's a 30-year typo that no one ever fixed. So it is refer with one R, even though that's not how you spell the word refer. Yes, I can spell, I swear. And if you log in and you type in your username and password into Facebook, your login request came from Facebook. But if an image tag on a forum makes you do that, then the refer header is going to say that it came from the forum. So yeah, that's basically like telling you like, is the request coming from my website or is it coming from somewhere else? However, we need to figure out like, how do we allow a request to go through, right? Because if I'm only allowing, the refer header is basically going to give us some information about where a request came from, and we then have to decide which requests we allow or don't allow based on the refer header. So maybe we only allow requests that come from the same exact website, right? So maybe like the refer header matches some sort of like expected URL. So for example, like if we're logging into a bank, I might expect it to come from bank.com/login, right? We can also disallow cross-site requests, right? So rather than just allowing, we can choose to ban anything coming from like a different website, right? So if the refer header doesn't really match the URL that we're expecting, then just ban it, right? So this is an example of just like one policy that we can follow, but honestly, working with refer headers is a lot more complicated than just this. So first of all, the refer header might leak some private information. For example, this is the example that we've used on the slides. Let's say that you're working at Apple and you're on like this like top secret website. Okay, the refer header. Okay, in this example, what are we doing? We're looking at iPhone competitors, right? So if I'm kind of like making a request from this like website, then I'm going to be leaking to whoever I'm making the request to that, first of all, Apple has a lot of like internal like websites that people aren't even supposed to know this link exists, right? But if I'm making a request, then I'm going to know not only does this website exist, but Apple's looking into competitors for iPhones, right? So this, I don't think Apple would appreciate if we did that. All right, so basically, another example here is that if you make a request to an advertiser, the refer header will give the advertiser information about like where you're seeing this ad. So another thing is because of these violations, the refer header could be removed, right? So that can help with like privacy and stuff. But then, right, so yeah, in this case, maybe the company firewall removes the header before we ever even send out a request. Or maybe, yeah, your own browser just like removes it based on privacy settings. Even so, the refer header is honestly optional, right? So essentially, what if we don't have anything in the refer header? Well, do we accept that or do we not accept that, right? Should we allow requests without a header? Well, in that case, it's less secure because, you know, you can maybe do a CSRF attack. Should we deny requests without a header? Well, in that case, a request that was like made legitimately could still be denied, right? So there's no right answer for this. And so honestly, refer headers can be like a little bit difficult to work with. So this is why a lot of servers don't really use refer headers. And if you do use a refer header, you need a good policy that makes sense. So yeah. Lastly, we're going to talk about the same site cookie attribute flag, right? So we can prevent CSRF attacks with the same site cookie attribute. And this is a browser level defense that is somewhat similar to like the refer header thing that we talked about. So in your cookie, we had a lot of attributes that we talked about. There was like the name, the value, the domain, the path, the expiration time. There's another attribute there called same site. And this is an extra flag that says that you can only send the cookie if you are on the same site that you're making the request to, right? So if I'm on google.com only like google.com related things are going to be like requested, right? So if I set same site equal to strict, then we're not going to attach the cookie if the cookie's domain does not exactly match the domain of the origin of the web page that triggered the request, right? So if I'm making a request to bank.com, I will only attach the cookie that on bank.com requests that were made from bank.com, right? Or else it's not valid. So this is enabled on most modern browsers. Some like older browsers or like different, less common browsers don't enable this, but yes, this is the same site attribute. So in summary of what we talked about today, I talked about a lot. So yes, happy to do questions after. Cookies are basically pieces of data that make HTTP requests stateful. They allow you to associate different requests with each other, and they have a lot of different attributes themselves. We also have a cookie policy that tells you what the server is allowed to set and what the browser is allowed to send. And they can also tell us which cookies to automatically attach to a request. Yes. Cookies can also be used for session authentications that multiple requests can kind of come from the same logged in user, right? So that was the Gmail example with sending emails, opening emails, etc. It kind of like allows for this notion of having sessions. So any request with a session token is associated with you. If someone steals it, they can impersonate you. So do not get your session token stolen and don't have your session tokens be guessable by attackers, or else you will allow people to be impersonated, and that's bad. And then also send your session tokens to the right place, or else you're going to allow other websites to have information that they're not supposed to know. We talked about an attack. We talked about CSRF. Basically, yes, it occurs when a user is tricked into making an unintended request that's forged by an attacker. Because cookies are automatically attached to your requests, it can look like the user made a request on purpose when they didn't actually do that. So yeah, we talked about doing this with GET requests. We talked about doing this with POST requests. And yeah, this was like an overview of the attack we just talked about. And then last slide of the day. These are the summaries of defenses we talked about. So we have this additional secret that we're generating called the CSRF token. And this can make it harder to like forge CSRF tokens themselves. And then we also have refer headers and same site attributes that basically prevent cross-site requests from kind of running. So thank you guys so much for coming. This is all I had. If you have anything else that you want to say, but thank you so much for your time. This was really fun and cool. And I should turn that off.
So that given that we finished 45 minutes early, and given that your exam is on Thursday, if people have exam related questions, we can take anything, whether that's like content questions or logistics questions. We can basically run like a Q&A if you guys want. You're also welcome to leave. That is all the content we're covering for today. You're also welcome to come take more cookies. But I'm here in theory for the next 45 minutes as long as someone else wants to be. So if people have questions, this is a great time to do that. Okay, I think I'm going to end the Zoom at this point. Thank you guys so much for coming. Bye.
I'm at a tavern. I'm trying to generate this, like, to generate